So yeah, let's talk about our today's agenda. So you're going to first get an overview on a new take to an old problem on calculating pi. So it's going to be a little bit of a history lesson and a little bit of a math lesson. And then you'll see a walkthrough of the prototype I wrote to try to calculate to beat the record for the most digits of pi calculated. And kind of spoiler alert, yeah, I didn't come close to breaking the record. But I think there's still some interesting takeaways from the prototype that I want to share with you, which will conclude the talk with where you can go from here. All right, so yeah, so a brief of a bit of a history lesson. Okay, so why do we calculate the digits of pi? And one way that we could think about it is that it's a way to track human progress. You know, and there is a book, The Art of Computer Programming, written by Donald Knuth, and where he mentions this. And if you think about it, like it's starting in 3000 BC with the Egyptians, they had pi around four and several digits. And then in 2000 BC, the Babylonians had it at 3 1/8. So it's starting to get closer. And then as we continue on in timeline, around 1500s, early 1500s, pre-calculus is introduced, and they have pi calculated to about 6 digits. And then as the math increases, like we get better, we get into calculus and differential equations, we're able to calculate pi with more and more accuracy, more and more digits. And then computing, it becomes exponential or even double exponential. I'll have to do the math, you know, no pun intended on that. But yeah, but when we start to get into computers, now we're calculating pi way more and more accurately. And so it kind of like begs the question for me, at least, is like every time when we look back in the timeline, as we discover as humanity, we discover new math equations and the math gets better, our accuracy of pi gets better. And now that we have like this raw computing horsepower, you know, I'm wondering are we going to see improvement? Like, is the math going to help us get pi more accurate, or is this computing going to help us get math to be better, where we could calculate more digits of pi? So hence, calculating the digits of pi is just a way to show our progress, our evolution throughout history. So why am I a part of this? Why am I calculating the digits of pi? Well, I was inspired by a teammate of mine, Emma. A few years ago in 2019, she calculated 31.4 million digits of pi. So 3.1415. She calculated 31.4 trillion. I see what you did there, Emma. But yeah, she used Google Cloud in a vertical scaling approach. So what does that mean? Well, first, let's talk about the tool that Emma used called Y-Cruncher. So you can go and look at this tool called Y-Cruncher right now. And it's kind of like the industry standard or the gold standard, you could say, for calculating pi. So it uses one algorithm to calculate the digits and then uses a separate algorithm to verify the results. And then it kind of produces this certificate of completion that, yes, it certifies that you were able to accurately calculate X number of digits of pi. And so what Emma did was she used a very, very, very big machine. So here you can see 96 V CPUs, and it took 121 days to calculate these 31.4 trillion digits. And to get an idea of how big 31.4 trillion digits is, if it took you 1 second to say a digit of pi, like 3, 1, 4, so that's 3 seconds for those 3 digits, it would take you 10 million years to say all the digits. So these are really big numbers here. And you can read more about her achievement in this article. And I was inspired by her work, but I'm on the serverless team. And so I kept on thinking, you know, what if there's a way to calculate the digits of pi in a distributed way? Could we break up the calculations somehow? And so we all did a quick my teammates and I, we did a quick, search, and what we found out was, could we find a formula to do this? If we could find a formula to break it up, we could scale this out. And to my amazement, I think to all of our amazement, but yeah, there actually is an algorithm to do this. And what's interesting about this algorithm is you say, hey, go get me the 1,000th digit of pi. Or you could say, give me a range of digits of pi. And you don't need to know any of the preceding digits. One caveat, though, is that it returns it in hexadecimal. So I like to think that I'm brewing for life, that if anyone asks me, hey, recite the digits of pi, I'm going to say 3.243F6 from now on. Yeah, so again, give an example of this algorithm. So if you were to say, give me the 1,000th to 1,005th digit of pi, it would produce 349F in Foxtrot 1. So we'll come back, and you don't need to know any of the previous digits. And a little side note that I thought that I discovered when I was researching this algorithm is that the Simpsons TV show actually used this algorithm. One of the characters needed to know the 40,000th digit of pi, and the writers asked this mathematician, hey, what is this digit? And so the mathematician printed out all 40,000 digits and sent them to the show writers, which was interesting. And then also, if you look at the first page of this of the research paper here, it mentions how that this algorithm was discovered by a computer program. And so I kind of go back to the timeline of like, as we get more and more computing horsepower, what are we going to discover with mathematics? And so that's just my personal interest in this. So it's just interesting stuff. Right? And so yeah, this is great. Like I'm getting this algorithm, like, okay, this is awesome. I work on cloud functions. I'm gonna spin up a function, like you go get this digit, this series of digits. You go to get this series of digits. This is great. What could possibly go wrong here? Well, the algorithm is a bit slow, as in n log n slow, which means it's slower than linear. So even like linear would double, like if we started off with 1 million, then 2 million to 4 million, if we were just at linear, the time would double. And n log n is actually slower than that. And right there, it was like, okay, this approach isn't really going to be the embarrassingly parallel workload that I thought it was going to be, that I would be able to compete with Y-Cruncher. But it was still kind of like interesting, and I wasn't going to let n log n, slow me down or stop me there. So I was going to build it anyway, and I was going to build it in Node.js. And I know what you're thinking, okay, why? That's an interesting choice. Why Node.js? And you might have heard the expression that any algorithm can be written in JavaScript will eventually be written in JavaScript. And I had to add, a little corollary to that, including the digits of pi. So I wanted to write it and implement this in Node.js. So thank you, my teammates, for putting up with that. Yeah, so let's look at some early test runs. And again, this is about the algorithm. So what I did initially was create a call function for HTTP requests to go and calculate the 1 millionth digit up to the 64th million digit, which happens to be delta. And you might be like, then when you look at the times, like 1 millionth is 41 seconds, and the 64th millionth digit was 54 minutes. Like I said, think of n log n slow. Now you might be thinking, wait, I've used cloud functions before. There's a max time of 9 minutes for an HTTP request. How are you getting this thing to run for 54 minutes? Well, we have in public preview now Cloud Functions 2nd Gen. And with 2nd Gen, you can have up to 60 minutes of HTTP processing time. And you'll hear me talk more about 2nd Gen later in the demo. Oops. All right, and then yeah, just to compare it to Y-Cruncher, which is, I tried to use compatible machines. So this was on a GCE instance. Yeah, it wasn't even close. Like it calculated all 64 million digits in 12 seconds, 12.7 seconds. And so yeah, it was just, there are faster algorithms for this type of what they would call a spigot algorithm, where it's kind of like a drop of water spigot. Like you can just say, get me just one digit or just a few digits. There are faster types of algorithms like that, but it was just nothing was going to compete with Right Cruncher. But again, like, no, let's do it anyway, and just let's build it and let's just have fun and see what happens. So what I'm going to do now is I'm going to stop sharing slides, and I'm going to share my screen, and we're going to kick off a run of calculating 100,000 digits, and which would take like several minutes. And then I'm going to go back to slides, walk you through the architecture, and by the time we're done going through the architecture, it should be done. So let me share my screen. Right. And so here I have a quick demo script, and I'm sending to a cloud function second gen. I'm sending 100,000 digits as a request and a section size of 50. So each one of these cloud functions that are going to be spun up are going to use that BPP algorithm to calculate section size of 50. And then it's a authenticated function, so I have to send in a header with a bearer token. Right, so let's run that. And while that is running, I'm going to go back to slides. Perfect. Okay, let's walk through the architecture while that's going in the background. Okay, so right now you saw me send a request to a cloud function second gen to process the incoming user request, right? And so what that's going to do is just going to divvy up the work. It's going to say, okay, you want 100,000 digits with section size of 50. So then it goes and breaks that up, and then it posts to PubSub the instructions for that offset and the size. And then I need a way, so this kind of using like a map reduce approach. So I'll need a controller to watch for all of these worker functions to complete calculating. And it's going to watch Firestore for the results to complete. So just like I like using Node.js for quick prototyping, I also wanted to use Firestore here for quick prototyping as well. I consider using Bigtable, but as soon as I realized that the algorithm was going to be the bottleneck, I decided just to stay with Firestore. And one of the things too that I want to call out is notice that I'm using Cloud Task to spin up Keep Watch, the controller function in the background. And when we get back to the demo, I'll show you some tips and tricks that we have. And in other words, you don't want that first cloud function process request just sitting there waiting. You want to provide a good user experience, whether it's your customer as a user or a developer. You want to let them know quickly, like, hey, we've processed your request. And so for something that's longer lived, you want to use a cloud task to spin up a quote unquote a background, a function running in the quote background, right? Now remember, we've already split up the work and we published it to PubSub. And so I'm publishing this to a topic called Calculate Pi. And it's going to spin up a ton of workers, and those worker functions are called Calculate Offset. And so they get their instructions, they use the BPP algorithm, and then they save their results to Firestore. And then that Keep Watch, as soon as all of the workers report in, it's going to then go and make an HTTP call out to combine results and a fourth cloud function, second gen function, and then it's going to take all the results from Firestore and combine it into one answer. And I decided just to use a plain text file for simplicity. You might say you could use a binary file to store these results, but again, for prototyping, I just wanted to use a text file. Right, and yeah, so that's it should be pretty close to it. So to the result. So I'm going to jump back to sharing my screen. we'll do. Okay, so now while the result is still going, I think I need another 30 seconds. Let's walk through these. These are the 4 functions that you just saw me go over in the architecture. So let's just do a kind of like a super quick overview. And now you notice this second gen here, and I'm happy to answer more questions in the Q&A portion as well. And one thing that also notice, you might say like, hey, this URL, it looks like Cloud Run. Yes, with second gen, it's actually built on top of Cloud Run. So you get extra functionality now with some new capabilities. And if you want to know more, I'm just going to jump over to this tab. If you go to Cloud Functions documentation and you scroll down past quick starts and samples, you'll see where we have all of our second gen documentation. And one of those new capabilities that you get with second gen, like I said, was the longer processing time. And so here, this is the entry point to this cloud function. And then this is the section where it kind of divvies up the work. But the key thing is it tells Firestore, hey, I'm a worker, my status is pending, which will get updated to completed once another cloud function finishes the calculation. And it publishes it to PubSub. And then we have to say, hey, keep watch, start keeping watch. And this is where you can, where we spin up the controller to watch for Firestore. And if you want more information on that, I wanted to point out this blog post that Martin, he's a customer support technician in Google Cloud. He focuses on cloud functions as well as I do. And so last in December, we wrote a series of blog posts together about common anti-patterns that we see and what to do instead. And so using or like using Cloud Tasks to run a cloud function was one of the ones that you can find there. So yeah, and so then let's just look at this. I also want to show this calculate pi offset. Just want to show Event Arc. So Event Arc is our new eventing platform, and it's based on cloud events, on the cloud event standard. And this is something else that you get with second gen. So this actually in the Event Arc allows you to get more than 90 new event sources by using cloud audit logs. And there's demos, for example, like suppose that you have a policy at your company that anytime an engineer creates or whoever creates a new VM, you want that person's username to be a label on that VM. Yeah, sure, you could tell the person, hey, don't forget to do it. But the best way to reduce human error is not ask someone to do it, you just automate it. So you can have a cloud function that as soon as you detect in the audit log, that's triggered by an audit log, hey, there's a new VM created, it just automatically labels it with that person's username or whatever is the requirement for your company. So lots of new stuff here. Again, I'm not happy to answer some questions during Q&A. So yeah, by this time we should have the result. So I'm just going to refresh this page. So this is the bucket. And so yeah, so here's the result. I'm happy to also look at a few more functions. But yeah, if we look here, this is 100,000 digits of pi in hexadecimal. And if this were, if I was testing directly, I would download it and I have some scripts to verify it. Or we could just spot check, certain places to see if the digits were correct. But yeah, if we walk backwards, if we look at Firestore, I'm just going to refresh this. Here you can see like status completed. So all the workers completed their status and their digits and the offset. Let's see, what other ones? So we talked about, oh yeah, let's talk about the keep watch function. So this was the controller function. And what I did was just every 10 seconds, check Firestore, see where it was. And as soon as, all the workers are done, I made this HTTP GET call to the fourth cloud function, which is over here. And have that tab open, which was combined results. So that was a function to function call. And then that one was the one that went through them all and I just put it into a writable stream and then stored it in a cloud storage bucket. So that is the demo code for that. Just double checking if there was anything else I wanted to show you all in this part of the demo. All right, so let's, and so yeah, all of this was done with second gen functions. All right, so I'm going to now stop sharing and go back to slides. All right, so we just saw the results. And all right, so yeah, so just kind of like some technical takeaways again. So I want to call out PubSub here. You saw that I had, that was the thing I was going to show was the cloud function. In case you're new to cloud functions, how it was subscribed to a PubSub topic. But for me, I didn't have to really like have deep knowledge of PubSub. I just needed to know, how do I post to how do I create a topic in PubSub, post to that topic, and create a cloud function that is subscribed to that topic. So just kind of like developer of how do I use it without becoming a mastery in using PubSub. So it just worked. It scaled. I didn't have to worry about, am I sending too much traffic? Am I do I need to configure anything? So from my point of view as a developer, things just worked. And then the other thing too with like cloud functions, how many cloud functions workers got spun up? I didn't have to worry about monitoring. Do I need more cloud function to be spun up or not? Google handles that because it's serverless. So I could just have one cloud function created that was listening to that topic, and Google handled the rest of like how many cloud function instances needed to be spun up to calculate those 100,000 digits of pi. And then lastly, yeah, you saw that there was longer, like it's possible to do more than 60 minutes of execution time for a HTTP triggered second gen function. Right, and so yeah, kind of like what's next? Where do we go from here? What's your call to action as audience members? All right, so first I would like to point you to pi.delivery. It's Emma, she has Pi as a service API. And after she did her 31.4 trillion, I want to say like within the next year, someone was able to get to 50 trillion. And we actually have the 50 trillion digits. She has a story about it on pi.delivery. And we serve those 50 trillion digits. And we also have some cute demos, like what does Pi sound like? What does the visualization look like? And that you can check out. And again, my personal interest in this is I keep asking the question, okay, we're now up to 50 trillion digits. What is in this thing? Seriously, we talk about like, yeah, pi is a non-repeating number, all this stuff, but it's like, yeah, but has anyone really checked? Yes, I know the math, I know the math isn't like the proofs and all that, but it's like, we need to spend some time looking at looking inside of this thing. But I bet there's some interesting numbers, like the 6 nines, like the 750th mark around there in pi. There's like 99999, like 6 nines. That person who found that was like, wait, is this starting to repeat? So you gotta, yeah. I'm just curious what's in there. And then, but at the end of the day, the take-home message for you all is how might you fan out, calculations for your CPU-intensive workloads, or if you have embarrassingly parallel workloads that are truly parallel that you could use, this type of map reduce approach. Like, how might you think about old problems and in a new way? And I want to call out, originally I thought I was going to call this parallel, what did I call this originally? Calculate pi in a parallel way, but then that was before someone had to point out to me, no, that this isn't parallelization, because the algorithm gets slower and slower the further out you go in pi. And I was like, oh yeah, that's a good point. And so that's why I called it distributed, but you might truly have parallel workloads that you can use. So that's your take home message. And yeah, let's see what we have in chat. All right, I think I see a question, perhaps. Okay, so the question is, if you're opening this as a service to the public, which won't have access to the GCS directly, how would you let them know it's done and direct them to the download the file? Any best practices? So for me, this prototype was just it's not going to be open. There's pi.delivery, which is truly pi as a service, which is the fully calculated. This was a proof of concept and just something fun, as someone who works on cloud functions day in, day out. I just wanted to try. It was almost halfway like a joke when I said, hey, I want to challenge you to the Guinness Book of World Records. What if I did this in a distributed way? So this was just a prototype. I could potentially make it into like a code lab or some sort of demo, but of how you might use, like, call function to function, or use a function to call a function running in quote the background using cloud task, or just like the pub sub. How to use pub sub. It could be more interesting as sample code than an actual service. Right. And then, yeah, some other things we didn't talk about with, as a way, in case there's other questions that I see that are sent to me that I can see. Something else, like another capability we haven't talked about in this demo with second gen is concurrency. There's concurrency, there's traffic splitting. What else is there? Larger instance sizes with second gen. So I encourage you to check out the documentation that we have. We have tutorials on how to try out these things like concurrency, traffic splitting, larger instance sizes. What other? Those are big. And then, yeah, of course, longer processing time for HTTP functions. Sometimes you just need a little bit more time than the 9 minutes. And I'm not seeing any other questions. And I might just start looking at some of the other tutorials for, yeah, so traffic splitting. So just like you would, yeah, I mentioned the cloud audit logs, like using event arc. But traffic splitting could be interesting if you want to, just like before, like you could have like maybe like before in Cloud Run, you could have something like you have a cloud function and you're using traffic splitting. So maybe you have like 1% of your traffic goes to the most recent version of the cloud function, and 99% goes to the previous one. And that way you can kind of do AP, like blue-green, that's it. Blue-green testing to make sure everything's working okay before you send all your traffic to the new cloud function. So, all right, that's, I think that's it in terms of questions, and then seeing anything else be sub to me. So thank you, thank you for your time, and I hope this is, it inspires you to think about like what are some new ways we can solve old problems or existing problems.